Here's to anyone who's ever looked up. The airheads. And the space cases.
Live long and prosper.
The flight fanatics. The armchair astronauts. And the casually curious. Here's to those who know the thrust in newtons of a Pratt & Whitney J75 turbojet engine. And those who silently ask, what's keeping this thing in the air? Here's to those who can list the name, mission history, and favorite breakfast of every Mercury astronaut. And those who've ever searched for, how does a toilet work in space? Here's to the people who know a P-38 Lightning from a P-51 Mustang. And the people who thought those were the names of cars. Those captivated by the miracle of flight. And those who are just happy to make their flight. So whatever captures your curiosity.
We choose to go to the moon.
Or propels you to new heights. When it comes to the sky, there's space for all of us.
Good evening. Welcome to the 2025 Exploring Space Lecture Series, sponsored by Aerojet Rocketdyne and L3 Harris Technologies Company and United Launch Alliance. I'm Dr. Emily Martin. I'm a research geologist here in the Center for Earth and Planetary Studies at the Smithsonian's National Air and Space Museum. This year, our lecture series has covered my favorite research topic, oceans. There are oceans all across our solar system. Some planets had oceans in the past. Some planets, or moons, still have oceans today. Tonight, our final lecture of this series will explore the ocean we are the most familiar with, Earth's ocean. But where did all that water come from? Our speaker tonight, Dr. Kathy Mandt, is a leader in the field of planetary science. She is an expert in the origin and evolution of volatiles like water, across our solar system, and even into other solar systems. This means that Dr. Mandt's work is really important for understanding the formation of planets and their environments, like planetary atmospheres and planetary interiors, and habitability. Dr. Kathy Mandt is a planetary scientist at the Planetary Systems Laboratory at NASA's Goddard Space Flight Center. Dr. Mandt has worked across the solar system, and when I say across the solar system, I really mean across the solar system. And here are some of my favorite highlights. It's a highlight reel. It's not all inclusive, it's not everything. Dr. Mandt is a co-I on the Lunar Reconnaissance Orbiter Lyman Alpha Mapping Project, as well as the lead for the volatiles team on the Lunar Reconnaissance Orbiter. She was a science team member on the neutron mass spectrometer on the Cassini mission to the Saturn system, hey Saturn, and a member of the science team for the Europa Clipper's plasma instrument for magnetic sounding. For those of you that spells PIMS. Dr. Mandt was also a science team member for the ion and electron spectrometer on the I have Europa on the mind, I'm so excited. On the European Space Agency's Rosetta mission to, guys, I've practiced, 67P Churyumov-Gerasimenko. I got it wrong, Gerasimenko. And was the liaison to Rosetta's orbiter spectrometer for ion and neutral analysis mass spectrometer team. And Dr. Mandt is on the committee coordinating teamwork between NASA's Europa Clipper mission and the European Space Agency's JUICE mission to explore Jupiter's icy moons. Space science loves an international collaboration. Tonight, Dr. Mandt will be presenting her talk, The Origin of Earth's Oceans. It is my pleasure to present to you all Dr. Kathy Mandt.
Wow, thank you for that amazing introduction. And thank you, everyone, for being here. I think, yes, this is my first slide. This is, for me, a great honor to be here in this museum, which it's one of the most visited museums in the world, and it really showcases our love of space and our love of science. And it encompasses what I have devoted my life to doing. So I'm really honored to have the opportunity to be here and share with you some of my work. So today I'll be talking about the origin of Earth's oceans. And as she said, it's going to be the final one in a series about water, water everywhere. We're coming home to Earth. Now, Earth is the only planet that we know has life. We have been searching for life for decades, for centuries. We've thought we saw canals on Mars at one point. But to this day, the only place where we know that life actually exists is Earth. So it's our home. It's the most important planet, and I'm honored to be able to bring us back home for this series. The reason that we have life on Earth, and the only type of life we know is Earth-like life, so that's kind of our frame of reference when we're searching for life, but there could be other types of life out there. But the reason that we have life here on Earth is that there is liquid water on the surface of the Earth. Water is vital for life to be able to exist here on Earth. But the big question that a lot of scientists have had, looking at how planets form and how solar systems form, is how did Earth get its water? So I'm going to walk through what our understanding is of the process of the formation of the solar system, and you'll understand why that's a big question as I go through what we understand about that process. So this is one of my favorite visuals that has been created by NASA for our public education and outreach website. And it's a really good illustration of our current understanding of how the solar system formed. And we've gained this understanding not by going back in time and seeing what our solar system was like when it first formed. We don't have that technology. But instead what we do is we look beyond our solar system and we find planets forming in other systems. So we use what information we can glean from studying other systems to piece together the history of our own system. So what we know from studying dark clouds is that that's the beginning. There's this dark cloud of gas and dust. And that dark cloud at some point has some instability that causes all of the material, or the vast majority of the material, to collapse into the center of the cloud. That collapse will create a proto-sun or a proto-star. And as the star is in the process of formation, there's leftover material, just a very small fraction of what was actually in that dark cloud. But that material ends up forming a disk that rotates around that protostar. And over time, over about 100 million years, it's not a very long process, but that leftover material, the remnants, ends up combining and forming planets. And for the majority of the history of our own solar system, it's looked like it looks today, for the most part. We do know that it didn't form this way. In particular, the giant planets are very important. We know that they did not form where they're currently located, but they actually formed someplace else, and they migrated to their current location. We are still trying to understand whether they formed closer to the sun or farther from the sun, and there's also the possibility that Uranus and Neptune may have actually traded places when they were moving around. And in this process, when the giant planets were moving around, there was a lot of debris left over from forming the planets. And this debris we still have in our solar system. Those are asteroids and comets. But when the giant planets moved around, they scattered everything. And that's how we ended up with the asteroid belt where it is. We have the Kuiper belt, which is beyond the orbit of Uranus and Neptune. That's the trans-Neptunian area. And then there's Oort cloud, which is about 1,000 times the distance of the Earth from the sun. So that's very far out. And these bodies are very important because they are things that we can study right now, when we can take measurements of these small bodies and treat them as time capsules, because they haven't changed very much since the formation of the solar system. So they are something that we can use as a key to look backwards in time, since we don't have a time machine, and understand how the solar system formed based on measuring these small bodies. Now, getting to water. Water is one of the most important molecules because it is the basis for life here on Earth. And water is really special because it was also very abundant in that disk where the planets were forming. And water has this fingerprint that we're able to use to figure out what temperature conditions any water ice formed. Now, I'm starting to get into more of the technical graphs here. On the top left is a cross-section of what the disk looked like when the planets were forming. And what's most important about this illustration is it shows that it was warmest close to the sun, and as you get farther away from the sun, it starts to get colder and colder. And there's a couple of lines on the right part of that graph that are important to note. One of them is the water ice line. That is the point, the distance from the sun, which we think is about where Jupiter is today, maybe a little inward of Jupiter. But that point, beyond it, water ice could form. So inside of it, it was just rocky material forming to form the planets, and outside of it, there was a mixture of rock and ice, so you would end up with very water-rich objects forming. And then there's another ice line on that chart that's called the carbon monoxide line. Carbon monoxide is a very volatile molecule, so it requires even colder temperatures, very cold temperatures, to be able to form a solid ice. But beyond that line in the solar system, there are objects that formed with carbon monoxide ice. What we focus on for water is its fingerprint, which is in the form of isotope ratios. Water is made of three atoms, 2 hydrogen atoms and 1 oxygen atom. And hydrogen is normally a proton with an electron orbiting around the proton. But there's a rare form of hydrogen where you have a neutron or in the center in that nucleus, and that makes that hydrogen atom weigh twice as much as the most common form of hydrogen, and we call that deuterium. And the amount of deuterium that is mixed in with water in various places in the solar system is able to tell us what temperature water ice formed at. The more deuterium that's present, the colder the temperature conditions that water ice formed. So this is a fingerprint that we use to try and figure out the source of water for different objects in the solar system. Now, returning to Earth, we know that Earth formed inside the water ice line. So when we formed, we didn't form the rocks that ended up combining to create the Earth. Didn't have a lot of water at all. There were rocks, the rocky material did absorb small amounts of water that ended up coming up in volcanoes later, but there really wasn't enough to explain how much water is on the surface of the Earth right now. Comets and asteroids formed beyond the water ice line, and they were very rich in ice. Asteroids now don't have as much water, but they show evidence of water processing, so we know that they formed with some water. And then comets are a mixture of dust and ice, so they're very rich in water, and these objects are very important. We have found some comets here in our solar system that have a large amount of carbon monoxide, far more than most comets. And we call these carbon-rich comets, and we think that they formed outside of the carbon monoxide ice line, so they formed really far away. But we also think that when the giant planets moved around, most of these carbon-rich comets ended up being scattered outside of the solar system. And then when the giant planets moved around, other bodies got scattered inward and outward. And so this process is important, and this kind of, we piece together all of these things to to try and understand the full history of our solar system. We can't just take a look at one planet or one object. We have to take a comprehensive context view of the solar system as a whole. So the majority of the water that we here have on Earth now, we believe was delivered when the giant planets moved around and scattered these water-rich bodies inward to where they impacted Venus, Earth, and Mars. And all three of these planets, we believe, got their water delivered by comets and asteroids. What we don't know is how much of that water came from asteroids and how much of that water came from comets. We do know that asteroids formed closer to the sun and that comets formed farther out, and then there's some special comets that formed even farther out beyond that are carbon rich. But we don't have enough information to know how much of each of those types of small bodies did this. So we use the deuterium to hydrogen ratio in Earth's water and compare it to measurements that we make in the solar system of materials that serve as analogs for the potential sources of Earth water. Now, the D to H in the sun is a very low value. There's not very much deuterium in the sun. And we believe that any water that was in the region where the Earth formed had a value similar to solar water, because that water had evaporated from ice and it was mixing with molecular hydrogen, and they ended up sharing the same D to H value. So that would have a very, very low value. We get a sense for the D to H ratio in asteroids by looking at meteorites, and a special type of meteorite called chondrites. These are organic rich materials that are from the formation of the solar system, and the D to H ratio in most chondrites is very similar to the value that we have here on Earth in our oceans. So that seems like pretty good evidence that the majority of our water could have come from asteroids and not comets. We have some measurements of comets, but we aren't able to take measurements of comets like we are with asteroids with meteorites. We have to take images of the coma of a comet and try to measure what's in that coma to figure out what the D to H ratio is in a comet, and even then we're only getting the value of the water ice in that comet. But the few that we've been able to observe have a higher on average D to H ratio than the Earth's water. So that seems to be pointing at comets not providing the majority of the Earth's water. However, if you look at the individual D to H ratios, and I know this is an eye chart here, but what I'm showing in blue is the individual measurements of D to H in comets, all the ones that are available, compared to other objects in the solar system. And if you look at the D to H ratios in comets, they vary significantly by a factor of 4 to 5. So one comet can have a 4 times higher D to H ratio than another comet. And there are two classes of comets. There's Oort cloud comets, which we believe came from the Oort cloud, which is 1,000 times the distance of the Earth from the sun. And they have long periods, and they're very bright objects. So the majority of these measurements have been made in Oort cloud comets because it's been easy to make measurements in them. And on average, their D to H ratio looks like it's about 3 times the Earth's D to H ratio. A few years ago, we finally managed to get a D to H measurement in the other type of comet, which we call Jupiter family comets. Those are short period comets that maybe just take about 5 years to travel around the sun compared to 70 to 100 or a few hundred years. And that ratio was a big surprise because it had the same D to H ratio as the Earth's water, which opened up a whole new line of questions of whether this type of comet, Jupiter family comets, could have provided a significant amount of water to the Earth. So this is where we get into the European Space Agency's Rosetta mission. This was an amazing mission that was designed to go to a comet and use it as a sort of Rosetta Stone to help us understand the history of the solar system. This is our time capsule that we're looking at to go backwards in time and look at the formation of the solar system. NASA contributed 3 instruments to this spacecraft, and I had the opportunity to work on one of these instrument teams, so it was a really amazing international collaboration. And it is the only mission that has ever rendezvoused with a comet, landed on a comet, and then escorted that comet for 2 years as it went close to the sun and then back out again. So it was a groundbreaking mission. The instrument that was key to understanding the time capsule aspect of a comet for understanding the history of the formation of the solar system was the Rosetta instrument. This instrument was made up of 3 components, and the majority of them were built at the University of Bern in Switzerland, but US universities also provided components of these instruments, so it was also within an international collaboration mission. The instrument itself was an international collaboration between industry here in the US and in Europe. And this instrument, the one on the bottom right, was the most important for making these measurements because it's a mass spectrometer, which takes in an amount of gas, looks at the molecules that is in that gas, actually sniffs or tastes the gas, and figures out how much of each molecule is present. And it's probably the highest mass resolution mass spectrometer that's ever flown in space. We've had several missions where we've used mass spectrometers because they're extremely valuable for understanding atmospheres and understanding things like comets. And one of the primary measurements that this instrument was designed to make was the D/H ratio in water. So the Rosetta mission, like any mission that goes beyond Mars, was a very long-term mission. Anytime you go beyond Mars, this is something that we can't have humans do. We need robotic missions to explore beyond Mars. And even now, we can't send humans to Mars. We're still working on developing that technology. But going beyond Mars requires a long time to get there. And a comet is especially difficult because the orbit of a comet is unique. It's very elliptical, so they go very far out from the sun at aphelion. This one went out farther than the orbit of Jupiter. And then when they come in for perihelion, that's the closest distance from the sun. That is around Earth's orbit for this comet. Now, so what happened with this mission was it launched in 2004, and it took 10 years and 4 gravity assists, and we had to put the spacecraft into hibernation because it got too far from the sun for the solar panels to be able to power the spacecraft. So the only thing that was powered on the spacecraft for a brief period of time was a clock that was designed to wake the spacecraft up when it was close enough to the sun again to be able to operate. And this was one of the scariest things because nobody had ever done this with a spacecraft where we put it to sleep and just hope it wakes up. And we were quite lucky because it did, and we had a very successful mission. So it arrived in 2014. So if we can go to the next slide. Now, missions like this, robotic science exploration missions, are always full of surprises. We are sending robotic missions to places humans can't go, to places that we cannot see very well from Earth, that are new ground for us. And this was the first time we had ever visited this comet. So we had a series of surprises just within the first few weeks as we approached the comet. One of them was the appearance of the comet. What I'm showing here is what we expected the comet to look like based on Hubble Space Telescope observations of the nucleus. Now, at the time, the Hubble Space Telescope was the best observatory to be able to take any images of this. So this was the best of the best, what we could get. But as we started approaching the comet, we have a navigation camera that we use to actually navigate the spacecraft that returned these images that were very different from what we were expecting. We were expecting an object, not a duck. But once we discovered that it looked like a duck, we had way too much fun with it. We even would make these models of the comet so that we could like shine light and figure out which areas would be lit up and which areas would be in darkness, and we would study those. And we even had way too much fun with those models. But this was our little ducky, and we loved our little ducky. One of the other surprises was the type of activity that we observed at the comet. We knew that comets were releasing ice that was sublimating and flowing out, and that would be the activity that produces the coma that comets are most famous for. And that gas would lift up dust as well. One of the surprising things that we saw is that there are other activity drivers on the comet. This is showing 3 images from the navigation camera where they were taken 7 seconds apart, and between each of these, a jet suddenly appears and then suddenly disappears. So there's some sort of destabilizing activity in the nucleus that causes an outburst of water and dust and creates this jet that goes away quickly. And we still don't fully understand what drives this type of activity, but it was another one of the amazing surprises that we get from robotic missions. The other surprise about activity was how it affected the spacecraft. Now, we knew that as we got closer to the sun, the comet would become more active. When we first rendezvoused with the comet, it was inside the orbit of Jupiter, but it wasn't very active at all. So on this chart here that the European Space Agency created to illustrate the activity of the comet, we first arrived when it was more like just a little rock, maybe with a little gas coming off. But we stayed with the comet all the way around through perihelion, the closest point to the sun, and then all the way back out to where the activity died down again. So we saw the whole evolution of activity for the comet. And we knew that there would get to be a point where, when we first arrived, we mapped the comet. So we got within very close range and orbited and took all these pictures. But we had to move away because as more and more gas is coming out, and we have solar panels that are effectively like a sail, we would have to move away because it would be hard to control the spacecraft with all this gas flowing against those solar panels. And we knew we'd have to be prepared for that. So we thought about the effect of gas on the spacecraft. Now, our plan was when the activity got to be too much, we would move out to a safe distance, and then we would plan close flybys of the nucleus. So we would plan to fly into the coma, fly close to the nucleus, and then fly back out. And unfortunately, the very first time we did that, we discovered something that we had not considered. We used star trackers to control spacecraft. This is a pretty common tool for spacecraft to be able to figure out their orientation. So these star trackers take an image of the stars, compare those to a map of the stars, and that tells us where the spacecraft is pointed. Make sure that we're pointed at Earth. Make sure that the solar panels are pointed at the sun and we don't run out of power. But as we got close to the nucleus, we saw this, and we had forgotten the fact that there's a lot of dust in a coma, and that dust is icy, and when the sun shines on the dust, each dust grain looks like stars. So the very first time we tried to do this maneuver, the spacecraft got confused and went into safe mode, which is the scariest thing that can happen when you are in charge of a robotics mission. So it went into safe mode, moved back out, but we managed to recover the spacecraft and continue the mission, and we had to throw out all of our operations plans and rewrite everything with this new knowledge about the dust. Now, the dust is important in other ways, so you're going to see this come up later. The final big surprise that we got was the very first D to H ratio measurement in water. They made this measurement right away because there was water present, and it was one of the most important measurements. So we took that measurement right away, and it was a very high value. It didn't look anything like other Jupiter family comets, even though this comet is a Jupiter family comet. So we were expecting it to follow the trend of other Jupiter family comets, and it didn't. In fact, the D to H ratio that was measured ended up being higher than the average value for Oort cloud comets, so it was really weird to see. That would suggest that this, because the D to H ratio is really high, that would suggest that this comet formed in really cold conditions, which ended up also confusing because we looked at other measurements that were made, like the carbon monoxide abundance compared to water, and this wasn't a carbon-rich comet, and it should have been a carbon-rich comet with this high of a D to H ratio. So a lot of things about this measurement didn't make sense. It was another big surprise. Now I'm really going to dig into the data, so I hope nobody's eyes glaze over. But what's important about these two figures, the figure on the left illustrates what the data looks like that we use to measure the D to H ratio. What we have to do is take all of the molecules that have a mass of 19 atomic mass units to try and find HDO, water with deuterium. And we have to separate them according to their mass, but there's 5 different species in that mass range. And what's really frustrating about deuterated water is it's in that third peak on the right of this figure, and it overlaps with water that has a heavy oxygen instead. So oxygen normally weighs 16 atomic mass units, but there is an isotope of oxygen that weighs 17. So H217O and HDO weigh the same, and they weigh close enough to the same that they overlap in their signal of this. So analyzing this data was extremely challenging. We would take a spreadsheet and play around with these numbers, and analyzing a single data point would take weeks. So up to the point where we started working with the data, there were only about 150 data points that had been analyzed because of how difficult it was. But then I met Jake, who is an exoplanet scientist, and he's been using this method called Bayesian nested sampling, which I won't explain because I'm not an expert in. But he's using this to take data from JWST on exoplanets and try and figure out the probability of different molecules actually being present in an atmosphere that JWST is observing. And this is a more statistically robust way of separating overlapping signals than what we were trying to do by hand using spreadsheets. It's also a lot faster, so we were able to take 16,000 individual measurements of the mass 19 and analyze those very quickly, and we found that 4,000 of them had a strong enough signal to noise and a good enough fit to the data that we could actually look at the variability of the D to H in the coma over the entire 2-year mission, which covered a wide range of distance from the sun and a wide range of distance from the nucleus. And that's what is shown in the figure on the right, where the top row is the D to H ratio, which varies a lot. And then below it is the oxygen isotope ratios, which we found also varied. And then the very bottom shows the distance from the sun in kind of a salmon color, and then the distance of the spacecraft from the nucleus of the comet over time. So you can see the point where we started to travel farther out from the nucleus and stayed farther out from the nucleus for a while. But because we were seeing so much variability, so you see there's all this variability, and we wanted to really try and understand why that's variability. And the reason that there's so much variability is what Rosetta was measuring. Usually when we measure a comet, we look at the whole coma from Earth using a telescope. So we get the big picture and we get the average value over the whole coma. When you're in a spacecraft in a coma, you're only measuring what's right by the spacecraft. And one of the things we knew coming in is that dust is covered in ice, and when that dust is released, that ice heats up and sublimates as well. So you have water in the coma that's coming from the nucleus, and we want to know the D-to-H ratio of the nucleus, not the dust. But then you've got that annoying little dust adding more water to the nucleus, and when you're in a spacecraft and you're surrounded by dust, how much are you measuring the dust, and how much are you measuring what's coming from the nucleus? And that was one of the things that we tried to figure out. Also, as we escorted the comet around the sun, we figured out that the dust has this unique cycle where it's recycled on the surface. So when the comet was close to the sun, the southern hemisphere would be in summer, and it would get really heated up, and a lot of dust would be removed and added to the coma. And as the comet moved back outward, certain areas of the comet were colder and in winter and shaded, and about 20% of that dust would re-land on the surface after releasing some water into the coma and stick to the surface all the way around back towards Jupiter. And then when the comet would come back to around the sun again, the northern hemisphere would be in summer. And so that old dust that had already been in the coma and then deposited was reactivated and would go back into the coma and add more water to the coma. So this cycle of dust, you have old dust and new dust, and different time periods would look very different. Now, and so this is an illustration looking at the comet itself of those three different phases of the dust cycle, where there's the southern summer, the redeposition, mostly around the neck of the duck, because that area was shaded, so it was colder, and the dust would land on it and stay because it was cold enough, and then it would be reactivated. And when we first saw the comet, the neck was where all the activity was coming from, and we realized, oh wow, this is old dust from the southern hemisphere. So that was a cool discovery as well, one of the many amazing things you learn with these robotic missions. So what we did when we had this data and we couldn't understand why there was so much crazy variability, we started looking at laboratory studies that had taken ice and mixed it with dust and sublimated that ice to try and simulate a comet environment, because we knew comets have dust. And what they found was that when they take ice and heat it up and the ice flows as gas through the dust, that the D-to-H ratio in the gas that had passed through the dust would be higher than the D-to-H ratio in the ice. And the reason that that happened was that deuterated water was sticking to the surface of the dust grains while regular water was being released. So the ice that forms on dust grains is inherently enriched in deuterium, which in the case of our comet means that when Rosetta is surrounded by dust that's giving off ice, we're getting extra deuterium from that dust. And when we looked at the measurements, another crazy eye chart, but when we mapped out the measurements during these different dust phases, we found that the D-to-H ratio varied the most when we were around old dust. It varied significantly compared to where there was less of that dust. And that if we moved outward, even during perihelion, the farther we got away, the lower the D-to-H ratio would be, which suggested we were moving away from the influence of dust, because eventually these dust particles are really small, and they would release their water and they would dry out. And so we would get to a point, if we're far enough away from the nucleus, that we could avoid the influence of the dust and see more of the gas that's just coming from the nucleus. So when we plotted the data as a function of distance from the nucleus itself, we found that at one point the D-to-H ratio would level out. And that's what we decided was the best representation of the D-to-H ratio of the nucleus itself. And that was quite a bit lower than the initial value that had been published. And in fact, it was closer to the value in the Earth's oceans, which now started to make sense. We have a D/H ratio that looks more like other Jupiter family comets. We have a D/H ratio that agrees with the amount of carbon monoxide in this comet. And we have a D/H ratio that reopens the question of whether Jupiter family comets could have been a major contributor of water to the Earth. And so with that, that's my last slide, and I can take questions.
Oh, it's on already. I better be careful with this. If you haven't already, scan that QR code up there. Do it. Type in your question, and they will come to me on my super duper iPad over here. And I will do everything I can to get through these questions. But also, I get to do what I want. So I'm going to ask you some of my own questions first. See, it's great having a microphone. I want to talk more about the difference between asteroids and comets. Mm-hmm. Because what's a Jupiter family comet? I think of as asteroids, rocky, comets from the Oort cloud are icy. You know, dirty snowballs is what we all learn in school. So what's happening with Jupiter family comets? Did they come from the Oort cloud? Are they kind of like an Oreo cookie style where like it's a half and half kind of mixture sandwich situation? Like how do we have a third kind that I didn't know about?
Yeah, so we're still trying to understand how each of these comets, each of these small bodies got to where they are. In fact, there are comets in the asteroid belt that are actually releasing water, and they're close enough to the sun, which we're still trying to figure out how they got there. But Jupiter family comets actually come from the Kuiper belt, which is just beyond Neptune, or it's in the region of the orbit of Neptune. And we call them, I think, Jupiter family comets because we believe that Jupiter has perturbed them from the Kuiper belt and caused them to move inward. So that's the origin of how they got to become comets and no longer Kuiper belts.
Okay, that's very helpful. I remember having a conversation with some colleagues once, and they were like, you know, it's kind of a fuzzy area where you draw the line between asteroid and comet. And I was like, oh, no.
We thought we knew.
I thought I knew.
Yes.
So much harder than I expected it to be.
Yeah.
Because, of course, asteroids have ice on them, and comets have rock in them, and it just got so much more complicated.
Yeah.
So to add complexity to that, I don't know if anybody else was thinking this, but if your D to H ratio, right, your deuterium to hydrogen ratio is like locked in when that ice freezes.
Yeah.
So it's your like thumbprint of where did you come from. But how locked in is it? Given that we have a lot of things in our solar system that didn't form in the places where we see them now. So how do we know how locked in that D to H ratio is so that when you go and do things like this, which is very cool, that you know you're sampling that origin story rather than the Voyager story?
Yeah.
I don't know. Like the places
Nature
it's been
versus nurture.
Right.
Yeah. Yes.
Perfect.
Well, we do believe, like deep within the nucleus, the ices of a comet do represent that nature side of things, the formation of those ices, where they formed in the protosolar nebula. But as our work has shown, dust can kind of confuse things, and you have these objects that come close to the sun, they heat up, there's mixing of gas with the dust and refreezing, and then they come back out. And they heat up into a certain depth, so there's also loss of volatiles like carbon monoxide that don't need as much heating, so they end up getting pulled out of the nucleus at a much earlier stage than water. So we don't know exactly how much these comets originated with carbon monoxide compared to water, because they may have lost some from the nurture side of things, from heating up and coming back out. So this is an area that is open for investigation, and it's also a question that we now have with a lot of other comet measurements, because most of those measurements that I've shown are a single measurement where we looked at the coma from Earth and we got the measurement. But if it changes from one point to the next in the orbit, or if that happened to be a very dusty period with a lot of old dust, maybe we're seeing an enriched value because of the effect of dust and that interaction on the surface.
And you know how important that dust interaction is now. Because of Rosetta.
Yes.
So before, during, after Rosetta, when you, royal you, capital YU, are looking at these kinds of small bodies, comets, telescopically, so either using Earth-based telescopes or space-based telescopes, and you're looking at the coma, are you getting kind of an average? Now that we know how complex an individual system is around an individual comet, what is it that you're measuring, and how do you now take what you know from Rosetta and apply it to these slightly more accessible telescopic observations?
So what we do believe, what we have been believing, is that when we take a picture of the whole coma, that the bulk average is probably representative of what's in the nucleus. But what we've found out about comets is that the importance of dust in a comet coma is different from one comet to the next as well. There are some comets like Rosetta, or Rosetta's target, 67P, which dust isn't really that important if you look at it from a distance. There's not so much dust that it changes what you see from a distance. But then there's other comets that have so much dust adding to the coma that when you look at them from a distance, then it's very likely that a large proportion of the signal that you're seeing is actually originally from dust. So one comet is different from the next, and you can't make that assumption unless you understand the role of dust.
So I'm so sorry for this question. Where is the dust coming from? Is it like space dust, or is
that's
right, or is it dust that's sort of partially getting thrown off of the comet because of all of these jets that are, the sublimate, and it, say more, I want to say less.
Well, that's where it comes to that icy dust ball. When we first sent a spacecraft to a comet, we were expecting to see a big white object that's mostly ice. And these robotic missions are always teaching us so many amazing new things. We realized that it's actually a ball of dust that happens to have enough ice to create a coma. And that was because we sent a camera out there to take pictures, and we saw how much dust was in this nucleus. And so the dust is the more common part of the nucleus, but the gas is kind of like the engine for lifting the dust off of the surface. And then when we look at a comet, like if you look through a telescope and you see the coma, what you're seeing is the dust, not the actual gas, but it's there because of the gas.
I totally planted this question and hopefully planted a slide. You did a great job telling us about Rosetta and a lot of amazing things that Rosetta did. But we didn't get to talk about the Philae lander, which, if you believe the cartoons,
Philae.
And you believe the cartoons of the Philae lander visiting this rubber ducky, it's like the cutest animation.
Yes.
Oh my God. His little backpack, his little explorer. I love it.
Heading off to school.
Was there data that came from the Philae lander that helped? Oh God, it's so cute. That really helped with the reevaluation that you were doing and the kind of re-exploration of these data?
Not yet. So Philae was quite interesting because when you have a spacecraft in space for 10 years, you don't know if everything's going to work 10 years later, especially after you put it in hibernation. And Philae was supposed to have these jets on top, like motors that would push it down so that it would land on the surface and stay put. And then a harpoon that would shoot into the surface and hold the lander in place. And we knew before we released the lander, because we had checked out all the systems, that those jets on the top of the lander weren't going to work. Something had gone wrong in those 10 years in space, which everything else seemed to be working fine, so we decided to go anyway. But then as we released it and then it landed on the ground, the magnetometer, which it's amazing what you can get from magnetic field measurements, but our magnetometer realized it didn't stay put. It bounced and then landed and then bounced again and then finally landed on its side. So we didn't get all of the data that we had hoped to from this. And the reason that it bounced, well, actually, we actually got lucky because the harpoon didn't work either. And when the lander was on its side, it did have this MUPUS instrument, which was basically a hammer that would hammer the surface and feel how hard the surface was. And we figured the surface would crack pretty easily because it's ice and dust. But then it would hammer the nucleus and it couldn't break through with the hammer. They ended up going into and I was following this on Twitter because Twitter was great for science communication through this event. And the instrument itself had a Twitter account and they were tweeting, "No, not mode 3, which is the mode that would basically break the hammer if you hammer it hard enough and it didn't go through. They never broke through. Thankfully, the harpoon didn't work, because had we not had the jets working and the harpoon didn't work, we would have shot off the harpoon and shot ourselves into space and not gotten any data from the surface at all. So space exploration is pretty amazing, even with robotic space exploration. But we did get some data on the dust. They measured some dust composition, and that's something that we're going to look back at now. But they weren't able to really measure the D/H in the water on the surface.
Yeah. I mean, the drama of space exploration and how it was really sort of anthropomorphized in a lot of these illustrations that they were putting together, I think was just such a brilliant tool to get everybody really deeply invested in something that I think maybe otherwise they wouldn't have been. And I think it was such a great illustration of how to really engage people in these stories, because the drama is good. I mean, it is exciting. It is heart pound. I mean, it is really exciting to watch. And if you've never watched a launch, streamed a launch on NASA TV, do it. It's so good. I mean, the number of times I've streamed the collection of the Bennu samples from the Utah desert, and just, maybe we're just nerds. It's gripping TV. You should do it. I mean, it's completely unscripted reality television. I mean, it's about as good as it gets. Yeah. And I want to talk a little bit more about samples, because sample science is a big thing that's having I don't want to call it a moment, because it's been a long time coming for sample science to kind of regain some of the traction that it really has deserved over the years in terms of the problems that we've solved with sample science. And you talked very briefly about samples, meteorites, and doing tests on meteorites. And I'm wondering if you have anything that you're really looking forward to learning with respect to, whether it's small bodies, whether it's learning about our Earth, with any of this upcoming sample science or any new meteorite falls that maybe are really exciting.
So I think the thing that I'm personally most excited about is the Artemis missions and the possibility of returning ice from the south poles of the moon and studying the composition of that ice, because that ice may have come from a comet, or it may have come from asteroids. It may have come from volcanoes billions of years ago in the moon itself. And so returning samples of ice from the moon with the Artemis mission, that's part of the goals of the Artemis missions that are coming up, not just one, but we have multiple that have been planned or are in design. And I would really love to know the composition of those ices, not just the water and the D/H ratio, but there's noble gases mixed in, and there's other molecules like methane and carbon monoxide. And all of that material can tell us something about whether it came from a comet or something else.
Since we're going a little into the future, right? We
Yeah.
talked about sample science. We have a great sample collection now. I think now that we've done so much work on those samples,
Yeah.
we're ready kind of for this new batch.
Yes.
But there's some other really exciting missions that are en route right now to small bodies. I think small bodies is really having this,
Yeah.
I don't want to say moment again because it's redundant, but also not true. Like, small bodies, I think, are getting their due diligence now in
are.
the Lucy mission, the
Yeah.
Psyche mission. I'm certain I'm missing another one.
Yeah.
We just, completed a few years ago the Ceres
Yeah.
Ceres and
Yeah.
Vesta, right? The Dawn mission. Lucy and Psyche, I think, have some really cool stuff coming down the pipeline. Is there
Yeah.
something about one of those missions that, like, you're really looking forward to results on?
Yeah. Well, I think Lucy is really interesting because they've already done 2 flybys of asteroids, but neither of these asteroids are the actual targets of these missions. They've done these flybys entirely to practice operating the spacecraft and operating the instruments. Yet our very first one of Dinkinish, we discovered it had a moon, and that moon was kind of like our duck bilobate. And we never expected that this asteroid would have a moon and that the moon would be weird. So here we are just practicing operating the spacecraft, and we make this amazing new discovery of this really small body that nobody really thought was even important to study, and it's got a moon, and it's bilobate. So, and then there was just recently the flyby of Donald Johanson, which was also, again, just a practice, and they found that it was bilobate. And we're starting to understand more about the formation of the solar system, not just how ices form and the temperature and the composition, but also the dynamics of these bodies moving around. To form an object that's bilobate, they probably had to be moving slowly relative to each other and collided slowly so that they didn't break each other apart and just stuck together. And that has been surprising, but it's telling us about how quickly objects moved during this process when they were starting to build up together.
So I'm going to circle back on oceans because it sounds like
Yeah.
Earth got at least a lot of its ocean water from things like comets.
Mm-hmm.
Wild guess, how many 67 Ps needed to hit the Earth?
I think I'm going
Or
to
about
avoid
how much
making a
time
guess.
would it have taken? Because this is a lot. I mean, it's a
That's
lot
too
of
much
water.
math-
So
math
sorry.
to do
So
live.
sorry. I think Gina DiBraccio was measuring things in giraffes. But like, I mean, how? Did it?
Yeah.
Did we get all this water right at once as the Earth was forming and just like sweeping
Yeah.
up all of these icy things, or is it a longer process? Maybe that's a better question.
Yeah. We think that there was a period of time where this happened, and it hasn't been happening as much recently, which is good, because if we have a comet impact the Earth right now, we think that is what killed the dinosaurs. We don't want to live through that. So we think there was a period of time where there were a lot more impacts in the inner solar system. And one of the things that we do, we use the moon as kind of like a cornerstone for understanding that history of the solar system. Here on Earth, we don't have many impact craters, so we don't know the history of impacts on Earth. But on the moon, we see all these craters, and if we figure out the age of each of the craters, we know the time periods when most impacts happened. So the moon is, again, a connection for understanding the history of the Earth and when we got our oceans, because that would be that time period. When all those craters formed on the moon was when we got all of our water, or the majority of it.
I just saw this question pop up, and I really want to know the answer to it. What powered the clock on Rosetta when it went into hibernation?
I think it...
Do you
that
know?
I don't know.
It's okay.
I'm not going to
I'm assuming it's a really cool battery.
Yeah, it was
But-
either a battery or they might have gotten just enough power from the solar panels at that distance to keep the clock going.
Okay.
It worked, so I'm most happy about that.
So I have a 3D model of
Yeah.
67P in my office, which is great because I don't study
Yes.
comets, but I somehow have collected these like 3D printed models of all these
Yeah.
different small bodies across the solar system. And my 67P is about the same size as a rubber ducky.
Yeah.
How big is 67P actually?
Yeah. So from one end to the other, it's about 4 kilometers, which math again, live math is not
If you've ever
good
run a
in
5K,
miles.
it's about
Yeah.
like that.
Yeah, it's about so about 3 miles. Yes. My kids got me into the 5Ks. So
Great. Well,
Yeah.
thank you so much for this. I have a lot more questions, but everybody has a bedtime, I'm assuming. So I really want to thank you for this really awesome look at how Earth got its oceans. And it's been such a great sort of period to this lecture series we've had about water in our solar system in like its physical sort of oceanic form.
yeah.
I really want to thank again our sponsors, Aerojet Rocketdyne and L3 Harris Technologies Company and the United Launch Alliance for supporting the Exploring Space Lecture Series. And for those of you who are joining us here in the museum IRL, there is sidewalk stargazing tonight. This is a big deal. You should do it. It's right behind me at the Delta Solar Sculpture, which I'm sure a lot of you walked by. Don't go this way. You have to go out where you came in and walk down the sidewalk. But please do it. It's amazing. I'm sure there's some amazing things that they have out tonight to see, and I highly recommend it because if it's happening, it means the rain has stopped, so you can enjoy the outside. And while this is our last Exploring Space lecture for this year, our Airspace podcast team will be hosting Astronomy on Tap here at the museum next month, so please check out our website to learn more. I'll be there. And we really hope to see you next year for the upcoming Exploring Space Lecture Series in 2026. So check back later this fall for that lineup. And thank you so much for joining us this evening. Please get home safe.